Hello, I'm Srijan Das. I'm presenting VPN Learning Video Pose Embedding for Activities of Daily Living. This work has been done at NRIA. In this work, we are focusing on learning representations for activities of daily living. These videos are different from videos taken from the internet. Why so? Because these videos have no interclass variance. So videos pertaining to different classes have very similar visual appearances. Moreover, these videos have real-world challenges, one of that being no camera framing, which means the subject may not be centered within an image frame. This is not the case for the videos taken from the internet. Now let's discuss the challenges in ADN. One of the common challenges in all video representation problems is how to handle time. The next challenge is how to learn representations which are view invariant, because these videos are generally captured by fixed monitoring cameras from different views. So how can we learn representations which are invariant to multiple views? The next challenge is how can we learn representation of actions which have very subtle motion? And the last one is how to disambiguate the actions with very similar appearance, varying slightly along time. Such scenarios are very common in ADN. Just as the example we can see, wearing a shoe and taking off a shoe. If we go through the literature survey, most of the approaches have been validated on the videos taken from the web. The most popular and effective RGB-based approaches using 3D ConvNets like i3D, ResNext, slow-fast networks. But the problem with these networks are that the same spatio-temporal kernels are applied throughout the whole volume of the video. Thus, they are very rigid to capture subtle motion in ADN. Recently, non-local networks have been proposed on top of these 3D ConvNets. This non-local network applies a self-attention mechanism to modulate the existing visual feature map. But the problem is that it relies too much on the appearance of the actions and mostly work on when the motion of the action is high. On the other hand, if we look into the skeleton-based action recognition methods, nowadays people are using graph convolutional neural networks in order to make use of the spatial configuration of human body joints. But the problem is that these methods cannot incorporate the appearance information of the scene. Therefore, there are some methods that takes into account the advantages of the RGB cues and the 3D poses. So on the left-hand side, there is PI3D, where the skeletal information processed by RNN provides information about which part of the human body is relevant for recognizing an action. And on the right-hand side, there is separable STA, which is a two-stream network. One stream is responsible for providing a spatial attention for the image frames, and another stream is responsible for providing temporal attention weights to select the key frames in the video to recognize an action. But what these approaches are missing? One of the concerning factor is that there is no accurate correspondences between the 3D poses and the RGB cues in the state of the art. They tend to provide attention weights to RGB feature maps using 3D pose information without projecting them into the same 3D referential. The mapping is only done by cropping the person within the input RGB images. The next concern is that the state-of-the-art attention networks does not take into account the human topology, and none of these attention networks provide spatio-temporal attention weights, but mostly provide attention weights that are static throughout the video. That's why action pairs with similar appearance are often misclassified. So we aim at building a video pose embedding where we project the RGB cues and the 3D poses in the same referential. This will solve the issue of this misalignment problem between both the cues. And we expect that this kind of embedding can provide better learning of attention weights. That is why we propose VPN, Video Pose Network, on top of existing 3D ConvNets. This VPN modulates the visual feature map of the 3D ConvNets using the 3D poses which are robust to illumination and view changes. Thus, the proposed action recognition model consists of the video representation that is learned by the 3D ConvNet and VPN, which broadly consists of the attention network and the spatial embedding. And that is what we will go through. For the attention network, the input are the 3D poses and the output is the attention weights. But the question is, how do we leverage the spatial configuration of the human body? For that, we use a graph convolutional network. So the poses are first constructed to a graph using a weighted adjacency matrix. And then we employ a generic graph convolutional operation that computes the features f plus d at time instant t. Then we aggregate these features along time. Further, we apply some 2D convolutional operations to modern time. So we compute a latent pose-based feature vector H star. Now the question is, how do we learn the spatio-temporal attention weights? For this, we use a coupler. In order to learn a synchronized spatio-temporal attention weights, we learn the attention weights in two steps. First, we learn the spatial and temporal attention weights in two streams independently. Then, in the second step, we couple the attention weights by performing a Hadamard product. The corresponding output is now the spatio-temporal attention weights. Now, how do we learn the video pose embedding? In order to learn the video pose embedding, we project the representation of the video feature maps Fs and the latent feature vector from the poses Z1 into a low-dimensional embedding Fe and Pe, where Tv and Tp are the transformation matrices. And in this embedding space, we compute the distance between the features Fe and Pe. By minimizing this embedding loss, we strengthen the correspondences between the video and the poses. This embedding ensures that the pose information to be used for computing the spatial attention weights aligns with the content of the video. Now, how do we train VPN and 3D ConvNets jointly? Firstly, we employ the categorical cross-entropy loss to learn the classes. Then, we employ the embedding loss in the spatial embedding module. And finally, we employ an attention regularization to ensure that the attention weights are not biased to provide extremely high values to the parts of the spatio-temporal feature map with more relevance and completely neglecting the other parts. For the experiments, we have used 4 public datasets: NTU-60, its larger version NTU-120, a real-world human activity dataset Toyota Smarthome, and a comparatively small-scale dataset NUCLA. For the ablation studies, we have first shown the effectiveness of each component of VPN. As we can see here that the attention network followed by the spatial embedding significantly improves the action classification accuracy compared to the visual backbone, which is I3D. In the next step, we show that the different choices of the attention network with GCN or LSTM, with the coupler and without the coupler. We observe that the graph convolutional pose backbone and the spatio-temporal coupler is the best choice for VPN. We also performed experiments to show that the normalized Euclidean loss is the best choice for the embedding compared to the Kn divergence. Finally, we show that the spatial embedding that we have proposed improves significantly the spatial attention of the VPN. Next, we show some visualization. We show the heat map of the activations of the 3D joint coordinates which are computed at the output of the GCN. And we can see that for similar actions like hopping or jumping, different joints have been activated. And that's why VPN can distinguish between similar actions. And even we notice that for actions like thumbs up, which is localized into a small region in the image frames, the GCN can actually provide high activation to this particular joint, as you can see. Next, we show the TSNE plots of the feature spaces produced by I3D and VPN for some selected actions with similar appearance. It clearly shows the discriminative power of VPN for actions with similar appearance, which is a frequent challenge in ADA. We compare VPN to the state-of-the-art on NTU-60, NTU-120, Smarthome, and UCLA dataset. VPN outperforms on each of them. To conclude, we propose a novel video pose network which provides an accurate video pose embedding. We also show that this combination of embedding and attention network yields discriminative features, which is crucial for video understanding in general. And we also introduced an attention network that makes use of the human joint topology and a coupler that provides spatio-temporal attention weights. Thank you and stay safe.